Biodegradable plastics have been advertised as one solution to the plastic pollution problem bedeviling the world. But today's compostable plastic bags, utensils, and cup lids don't break down during typical composting and contaminate other recyclable plastics, creating headaches for recyclers. Most compostable plastics made primarily of the polyester known as polylactic acid or PLA end up in landfills and last as long as forever plastics. University of California Berkeley scientists have now invented a way to make these compostable plastics break down more easily with just heated water within a few weeks, solving a problem that has flummoxed the plastics industry and environmentalists. The researcher Ting Xu says that people are now prepared to move into biodegradable polymers for single-use plastics. But if it turns out that it creates more problems than it's worth, then the policy might revert back. And she says that they can solve this continuing problem of single-use plastics not being biodegradable. The new technology should theoretically be applicable to other types of polyester plastics, perhaps allowing the creation of compostable plastic containers, which currently are made of polyethylene, a type of polyolefin that does not degrade. The researcher thinks that polyolefin plastics are best turned into higher value products, not compost, and is working on ways to transform recycled polyolefin plastics for reuse. The new process involves embedding polyester-eating enzymes in the plastic as it is made. These enzymes are protected by a simple polymer wrapping that prevents the enzyme from untangling and becoming useless. When exposed to heat and water, the enzyme shrugs off its polymer shroud and starts chopping the plastic polymer into its building blocks, in the case of PLA, reducing it to lactic acid, which can feed the soil microbes in compost. The polymer wrapping also degrades. The process eliminates microplastics, a byproduct of many chemical degradation processes and a pollutant in its own right. Up to 98% of the plastic made using this technique degrades into small molecules. Plastics are designed not to break down during normal use, but that also means they don't break down after they are discarded. The most durable plastics have an almost crystal-like molecular structure, with polymer fibers aligned so tightly that water can't penetrate them, let alone microbes that might chew up the polymers, which are organic molecules. The researchers' idea was to embed nanoscale polymer-eating enzymes directly in a plastic or other material in a way that sequesters and protects them until the right conditions unleash them. In the year 2018, she showed how this works in practice. Her team embedded in a fiber mat an enzyme that degrades toxic organophosphate chemicals like those in insecticides and chemical warfare agents. When the mat was immersed in the chemical, the embedded enzyme broke down the organophosphate. Her key innovation was a way to protect the enzyme from falling apart, which proteins typically do outside of their normal environment, such as a living cell. She designed molecules she called random heteropolymers or RHPs that wrap around the enzyme and gently hold it together without restricting its natural flexibility. The RHPs are composed of 4 types of monomer subunits, each with chemical properties designed to interact with chemical groups on the surface of the specific enzyme. They degrade under ultraviolet light and are present at a concentration of less than 1% of the weight of the plastic, low enough not to be a problem. For the research reported in the Nature paper, her team used a similar technique enshrouding the enzyme in RHPs and embedding billions of these nanoparticles throughout plastic resin beads that are the starting point for all plastic manufacturing. She compares this process to embedding pigments in plastic to color them. The researchers showed that the RHP-shrouded enzymes did not change the character of the plastic, which could be melted and extruded into fibers like normal polyester plastic at temperatures around 170 degrees Celsius. To trigger degradation, it was necessary only to add water and a little heat. At room temperature, 80% of the modified PLA fibers degraded entirely within about 1 week. Degradation was faster at higher temperatures. Under industrial composting conditions, the modified PLA degraded within 6 days at 50 degrees Celsius. Another polyester plastic, PCl, polycaprolactone, degraded in 2 days under industrial composting conditions at 40 degrees Celsius. For PLA, she embedded an enzyme called proteinase K that chews PLA up into molecules of lactic acid. For PCl, she used lipase. Both are inexpensive and readily available enzymes. The quick degradation works well with municipal composting, which typically takes 60 to 90 days to turn food and plant waste into usable compost. Industrial composting at high temperatures takes less time, but the modified polyesters also break down faster at these temperatures. The researchers suspect that higher temperatures make the end-surrounded enzyme move around more, allowing it to more quickly find the end of a polymer chain and chew it up and then move on to the next chain. The RHP wrapped enzymes also tend to bind near the ends of polymer chains, keeping the enzymes near their targets. The modified polyesters do not degrade at lower temperatures or during brief periods of dampness. A polyester shirt made with this process would withstand sweat and washing at moderate temperatures, for example. Soaking in water for 3 months at room temperature did not cause the plastic to degrade. Soaking in lukewarm water does lead to degradation, as she and her team demonstrated. The researcher is developing RHP wrapped enzymes that can degrade other types of polyester plastic, but she also is modifying the RHP so that the degradation can be programmed to stop at a specific point and not completely destroy the material. This might be useful if the plastic were to be remelted and turned into new plastic. She said that programmed degradation could be the key to recycling many objects. Imagine using biodegradable glue to assemble computer circuits or even entire phones or electronics. Then, when you are done with them, dissolving the glue so that the devices fall apart and all the pieces can be reused.